In this screencast, we're going to look at two additional vector spaces associated with matrices. There's the null space and orthogonal complements of matrices. So the idea is the null space is precisely the set of solutions to A times a vector equals 0. Orthogonal complements will discover why it's the set of solutions to A transpose X equals 0. And so really, both of these vector spaces come from solving a system of equations on which the right-hand side is 0. Such a system is called a homogeneous system of equations. And our goal? To find bases for these vector spaces. So we're going to find bases for them. So in the first one, we want to solve AX equals 0. Well, that's the same thing as taking our matrix A and timesing it on the right by x, y, z, and letting it be 0, 0, 0. To solve that system, I just need to augment the matrix by 0, 0, 0, and then row reduce. Well, row reduction isn't going to change in any way, shape, or form the column of zeros. So whether I include them or not doesn't matter. I could just ignore them. So in order to solve that, well, when we look over here, we notice that the x and y are basic variables. Z, though, there's no pivot in this column, so z is free. So z is a free variable. I can rewrite this as x minus z equals 0, and y plus 2z is 0. If I solve each variable for z, I get x is z, y is negative 2z, and z is z. Which means if I take 1, negative 2, 1, and multiply it by z, I obtain all solutions to AX equaling 0. Well, that means that I have a basis. This vector right here, 1, 2, 1, 1, negative 2, 1, is a basis for the null space. So we've answered the first question. How do I find a basis for the null space? We row reduce. We take the free variables. We rewrite the solution in terms of the free variables, and the vector we obtain is precisely a basis for the null space. If there had been two free variables, if there had been two non-pivot columns, then I would have had two vectors in my basis. So we say here, since there's only one, that this is a one-dimensional vector space. And it's a one-dimensional vector space precisely because there's only one vector in a basis for that space. All other solutions are linear combinations of this vector. All right, we've got that null space down. Now we're going to go to orthogonal complements. First of all, remember, orthogonal is, there's a 90-degree angle, or that two vectors have a dot product of 0. Well, if I'm in 3D and I've got a vector, how many vectors are there orthogonal to that vector? Well, there's one there, one there, one there. There's a whole plane full of vectors orthogonal to a single vector. So if I have a vector, how do I find all vectors orthogonal to it? Or if I start, instead of with a vector, if I start with two vectors and consider the plane spanned by them, how do I find the one single vector or the line full of vectors that happens to be orthogonal to the plane? Our goal, how do you find the orthogonal complement? Here is a plane. Its orthogonal complement is the line orthogonal to every vector in the plane. Or if you have a plane, how do you find every vector orthogonal to it? How do you find the plane? If you start with a vector or a line, how do you find the plane of vectors orthogonal to it? That's our goal. We're going to start with just a simple example. Let's take the first column, 1, 2, 0. If I take 1, 2, 0, and I want to find all vectors orthogonal to it, one way to do that is just write x, y, z. If they're orthogonal, then the dot product should be 0. Well, that's the same thing as saying 1x plus 2y plus 0z needs to be 0. I can rewrite that in matrix form as 1, 2, 0 times x, y, z equals 0. Hold on, wait a minute. A matrix times a vector equals 0. That's a null space problem. But notice that my column 1, 2, 0 got turned on its side. I basically took the 1, 2, 0 and transposed it, which is why we're transposing things when we look for orthogonal complements. So the null space here, well, there's two free variables, y and z are free. So y equals y, z equals z, and x equals negative 2y. I'm just going to take the 2y and bring it onto the other side to start with. So that means that I could take negative 2, 1, 0 times y plus 0, 0, 1 times z. And this right here gives me all solutions to that problem. Notice that there are two vectors in a basis for all the vectors whose dot product with 1, 2, 0 is 0. So these two vectors right here are my basis vectors for the orthogonal complement of the vector 1, 2, 0. All right, well, if I start with a line, I've now produced a plane. The span of these two vectors is a plane, and I've started with a line and produced the plane orthogonal to it. Well, what if now I say all vectors orthogonal to all columns of A? So here's A. What now if I want all vectors that are orthogonal to every single one of the columns? Well, in that case, I transpose both. Not both, I transpose all three. And so when I take them and transpose all three, I take the columns, turn it on its side, take the column, turn it on its side, take the column, turn it on its side. And then I row reduce, out pops this matrix. This matrix right here is precisely the solutions to A transpose X is 0. And here Z is free, so we'll let Z be Z. Y is, if you add this to the other side, you have a 3/4 Z. And then I have an X equals, let's subtract the 3/2 to the other side. Notice I get a vector, minus 3/2, 3/4, 1. This is our basis vector for the orthogonal complement of A. And this vector is now a line. If you take the columns of this matrix and span them, they give you a plane, which means I want a single direction to give me all the vectors orthogonal to it. That completes the screencast.